Welcome. Today's video is about stability. As we advanced already in the previous video where we studied the transfer function and the impulse response. Now, this is super important in engineering, right? When you design something, you want that something not to explode when the final user is using it, right? Well, unless you design a bomb or something like that. Then you want it to be unstable. Well, I mean, under some circumstances, you want it to be unstable. Anyway, so imagine that you're designing something. I don't know, you're designing a perfect virtual reality system or whatever. But it so happens that if there's a small fluctuation coming from a power surge or something like that, then your system reacts by, the response that you get, the visual response that you get gets saturated and boom, it flashes and explodes in the head of the user. That'll be bad. And if you design that, you may be liable for damages. Anyway, so seriously, let's study what stability is, right? And for any system, remember that all dynamical systems are governed by differential equations. And the differential equations that govern these systems can tell you, right, if the system is going to go crazy when you have a small perturbation applied to the system, or if the system is going to be solid under perturbation. If there's a power surge, we want the system to absorb it and go back to where it was, not break down. All right. So, what do we call, when do we call a system stable? Well, let me give you a general notion. A system stable if its response to a perturbation dies out in time. So I want to, when I have inputs and output, I want my inputs to be controlled and my outputs to be faithful to the input. But if I do a perturbation, if I do an input for a little time, I want it not to get any memory. I want the system to forget about it. I want the system to react going back to what it was. I want it to dissipate the fluctuation, all right? Okay, you get the idea. If this pen is like this, it's not really very stable because even if it's in equilibrium, a small perturbation does that and takes it out of equilibrium. Now, of course, typically the plot that you get is that here's a system in a harmonic potential. Then you have, imagine a ball, for example. If you have it here and then you do a small perturbation and you move it like this, you kick it, a kid applies and kicks it, right? Then the ball moves like that, and then the ball goes like this, and eventually if there's friction, there's dissipation of energy, the ball will go back to the original configuration. That is stable. Now, if the ball is here, and then a kid kicks it, well, the ball is going to roll down the potential, and the ball is not going to go back to the original position. So that system is not stable, okay? If I'm going to say this is stable, this is unstable. All right. Okay, so the information about the stability of a system is actually contained in the transfer function. In a linear system, very easily, is contained in the transfer function. Remember, after all, the transfer function is the impulse response, right? So when I perturb a system from equilibrium by kicking it, whatever the system does the transfer function. And importantly, if you remember, the poles of the transfer function, remember that the poles of a function that is a rational function, numerator and denominator, the poles are the values of the variable for which the denominator is 0. So the divergence is like a polynomial kind of divergence, is 1 over polynomial kind of divergences, right? So the poles are the values of s for which the denominator of g of s is 0. And remember that that denominator is actually the characteristic polynomial that we saw. The denominator of the transfer function is always the characteristic polynomial for a linear system of constant coefficients. And that means that the poles of the transfer function are the roots of the characteristic polynomial. Now, studying the characteristic polynomial gives us a very good idea about the stability of the system. Before getting to a formal definition, let's collect in the form of a table the information that we've already been learning and we know about the relationship between the stability of a system and the roots of the characteristic polynomial. Shall we? Let's do it. A table. I summon the table! So here's the table. Now, remember when we studied second order linear ODEs, the roots of the characteristic polynomial could be in any of these categories. Now, I call the roots of the characteristic polynomial here as SR because S is the variable of the transfer function and they are also the poles of the transfer function, right? I call them lambda before. I will also call them all over the place. I'll call them eigenvalues a lot because they are eigenvalues. Yes, like those that you're probably studying right now in algebra. At the end of the course, when I'm sure that you've studied this in algebra, I will give you a little bit more of intuition how algebra and calculus are two sides of the same coin. In fact, calculus is just algebra in infinite dimensional spaces. Okay, but we will get there when we get there. For now, let's keep the task at hand. Keep to that. All right, so the kind of roots that you can get of the characteristic polynomial condition the kind of solutions that you would get if you perturb the system from equilibrium, right? Imagine that I take it out of equilibrium with some initial condition, which is kind of similar to kicking it with an impulse, right? All right, so let's analyze the nature of the solutions. What happens if you have a second order linear constant coefficient differential equation and you get a multiplicity 1 real root equals 0? Well, in that case, you know that the solution is the exponential of lambda t. Lambda is 0, so exponential of 0 is a constant. So in this case, it's a constant. What happens if the multiplicity is 2? Well, if the multiplicity is 2, that's easy as well, because what I get is e to the 0t, so 1 times c1 plus c2t. Oh, it's linear in t, it's a ramp. Right, so proportional to t. Okay, what happens if I get a real different from 0, a real part, a root that is negative, a negative root? Well, I know the solution would be if the multiplicity is 1, it's just the exponential of minus the, well, of lambda t, and lambda is negative, so it's an exponentially decaying function. And if the multiplicity is 2, well, it's the exponential function times c1 plus c2t, but that still is exponentially decaying, right? Even though there's a polynomial there, the exponential wins over the polynomial, and then you get exponential decay. All right. What happens if the root is real but has a positive real part? Well, it's a positive number. Well, the solution is of the form exponential of lambda t, or perhaps if the multiplicity is 2 exponential lambda t times a polynomial. But in any case, it's exponential growth because lambda is positive, so exponential growth. All right. Now, what happens if you get a purely imaginary root of multiplicity 1, right? Because you get that one, you cannot have multiplicity 2, it's the imaginary one and the conjugate, okay? Always a pair of complex conjugate roots, in this case, purely imaginary. Well, if it's purely imaginary, you get a cosine or a sine, right? This kind of solution. So oscillatory function multiplied by the exponential of 0 times t. So no exponential in there. It's just oscillatory functions in this case. Oscillations. All right. What happens if you get a pair of complex conjugate roots, but the real part is positive? Well, if the real part is positive, you get the sine and cosine multiplied by the exponential of the alpha t, alpha being the real part. And if alpha is positive, then you get exponentially amplified oscillations. Right? If I were to draw it, it's something like this. So you get, here's the exponential envelope, so the function will do this. Oscillating more and more, okay, as time goes. All right, how about when you have the real part less than 0 and the imaginary part different from 0? Well, then you get a pair of complex conjugate roots. The real part less than 0 means that alpha is negative, so I get an exponential of alpha t, alpha being negative, so it's exponentially suppressed, exponentially damped, oscillations. Right. So this is the case, for example, of the underdamped harmonic oscillator. So the solution in that case would look like something like that. You start oscillating like that, and then with an exponential envelope. You see, that's why I draw the envelope first, like this. Oh my God! Cut. Cut. We roll back to when it's exponentially damped oscillation. All right. Okay. So if I draw it, it's like the case of the underdamped harmonic oscillator, right? You get an exponential envelope, and then your oscillations are gonna go like that, dying eventually with the exponential. So this is the kind of solutions you would get. Now that we know, or we recall, the kind of solutions that you get associated to every root of the characteristic polynomial, if I perturb a little bit the system, let's think if the system is stable, if it's got some of those. For which one of them the system would be stable? If I make a perturbation and it results in a solution like that, in a response like this, which ones of these responses we can consider stable? Okay, let's begin from the easy ones. This one, a real negative root, exponential decay. Well, certainly this is a transient. If I perturb the system a bit, the response of the system will be perturbed, but then eventually it will die off. Imagine you're watching an old TV, and the old TV, you hit it or something, and the image goes like, but then stabilizes again and stays like that. That is what you would get in this case. So exponential decay, yes, is stable. All right, wonderful. How about this one, exponentially damped oscillations? Well, certainly the same thing, the saloon doors, right? You perturb it by going through, like an impulse. You see, that's the impulse response in a way. You enter fast and the doors go like bloop, 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 and eventually stop. So yeah, very fast, exponentially as well. So this one, exponentially damped oscillations, that's also stable. All right. Let's talk about oscillations. You get purely imaginary roots. Is that stable or not? Well, not quite. Imagine that I hit the TV and the image starts doing forever, starts oscillating forever. Or the saloon doors, I pass and the saloon doors go like and never stop. Your system is not stable under perturbations, it doesn't go back. Is this example that I said before, when you move it, but there's no friction. So it would be like and never going back to equilibrium. So no, that one is not stable. No. All right. How about that one? When you have a positive real root. Well, that means that you do a small perturbation and the response of the system is to grow exponentially. That would be the same as you pass through the doors in the saloon and doors go like boo, 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 and explode when the hinges cannot hold them anymore. Or you kick the TV and the image goes like usually you can associate this with catastrophic instabilities. In the case of exponential growth, you are definitely not stable. This is very, very unstable when you get exponential growth. Whatever you do, no matter how little, suddenly the system in time exponentially grows. It's a recipe for explosives. All right? Well, eventually something will break. That's what happens in practice. All right. Or saturates. If there's security mechanisms there, safety mechanisms, it will saturate them. And it will like, I don't know, jump some fuses or something. All right. Next one. Oh, we can do that one, exponentially amplified oscillations. What do you think? Actually, the one that I described with the saloon doors is more like this one, exponentially amplified oscillations. The other one in the saloon doors is I pass and the doors just go like, and explode, no matter how much the perturbation. And they can take a while. You pass, the doors go like that, and then go, and explode. With the exponentially amplified oscillations, it's precisely the picture I told you. You cross and they go like, and explode. All right? So certainly, that one is the case of no. Same as before, very unstable. The moment you have exponential growth of a small perturbation, well, be prepared for disaster. That's the recipe for explosions. All right. Okay, we have the rest to deal with. How about this one? Well, that one is linear growth. So yeah, this one, you cross the door and the door goes like, well, as in like saturates eventually because it hits the stoppers of the door by linearly changing its position more and more. So basically, you hit it and then starts moving at a linear pace, at a constant pace. So still definitely not stable. So this thing is not stable. It's not as dangerous as exponentially unstable, but it's certainly not stable. And finally, the constant one. That's the one that some people sometimes get wrong. They're both saying yes or no. Let me give you an example. You're watching TV. You hit the TV. And the image goes like, and now it's half the way out of the screen, and it doesn't come back. That is kind of a constant displacement. You see, that's not stable. If it's constant, you move it, stays there, but it doesn't go back to equilibrium, all right? So that thing is not stable. Now, if we have to, maybe this one I put 1 exclamation point. This one and this one have no exclamation point because these ones don't catastrophically grow. You see, this one grows, possibly catastrophically, but doesn't stop growing in time. These ones grow catastrophically. These ones are just not coming back to equilibrium. But not catastrophic, it's within bounds, right? In a bounded way. The oscillations are bounded, and the constant is just a constant displacement. Still not stable. Hope this is clear. Now, let's see. Of the cases where you have stability, what do they have in common? Well, they have in common this and this. That the real part of the roots is negative. Now, this, I told you for a second order linear, if you have higher order, of any order, is the same, because what could happen is you have higher multiplicities, but then still the exponentials dominate. When you get exponentials multiplied by polynomials, always the exponential dominates. And if the exponential is decaying, then it will control any polynomial growth at infinity. So, here we see what the recipe is for stability under small perturbations. We want in the system that all the solutions, that means all the roots of the characteristic polynomial, should have negative real parts, okay? So after understanding a little bit where this comes from, let me formalize the definition a little bit. Here's the formal definition. We call it bounded input, bounded output stability. That's the concept of stability. It's a simple notion of stability. Like if the input is bounded, then the output should be bounded too, and disappear in time in the way that we talked about. So this is BIBO stability. So, and the definition is a linear causal time invariant system with transfer function GS, that is a rational function, so numerator divided by some denominator that are polynomials, for which the degree of the numerator is less or equal than the degree of the denominator. It's BIBO stable if all the poles of the transfer function are on the left half of the complex plane. Taken to simple words, the algorithm you need to apply, a system is BIBO stable if the real parts of all the roots of the characteristic polynomial, the real part of all the eigenvalues of the differential equation are negative. All right, is that clear? Okay, so if I give you an equation and I ask you, is it stable? You have several options. You can solve the equation and see if all the solutions that you get are exponentially suppressed, which is what you need, as we saw. Or else, what you can do is, well, maybe I can find out the roots of the characteristic polynomial and check the real parts and see if they're negative. Now, that is simpler than solving the differential equation completely, but not much more. In fact, if I give you an order 7 equation, you need to find the roots of a 7th order polynomial, and that is tough. Instead, I'm going to give you a theorem that makes your life much easier to check if a system is stable. All right, let's see it. All right, so here's a very, very convenient, the Routh-Hurwitz criterion, very, very convenient theorem that I'm not going to prove. So I encourage you to research the proof. It's not too difficult, but it will take us a little bit off our path. It's a really, really convenient theorem that tells us, okay, you have a polynomial of degree n of real coefficients like this. Remember, this is organized slightly different than usual. A0 is the coefficient of the highest power, A1 the second highest, so on and so forth, and AN is the independent term, okay? Then, the roots, the real part of the roots are strictly negative if and only if, that's what this means, the sequence of determinants delta k, k equals 1 to n, defined below, are all positive for all k. So you need that all the delta k are larger than 0 for all k. And those are the determinants. To build these determinants, there's a recipe that is easy. Start with A1 on the left corner. When you move right, increase the subindex by 2. When you move down, decrease the subindex by 1. If you hit negative, it's a 0. If you get over the number of coefficients in the equation, it's a 0. We'll see plenty of examples in a minute, so we will see. It's important that you remember how to do determinants and not using Sarus's rule. I mean, you're doing algebra, so you will learn how to compute it with minors, because that's the right way to compute it. Because Sarus's rule only works for 2 by 2 and 3 by 3. It doesn't work outside that. So better do it always with minors. Let me just do an example of a determinant as an exercise, just to show you. If you have A, B, C, D, E, F, G, H, I, let's do this determinant. Okay, so it's important that you remember, by minors, pick a column or a row, whichever column you want, whichever row you want. They have signs associated with them, plus, minus, plus, minus, plus, alternating always, plus, minus, minus, plus, okay? So, the first one, this is equal to A and the minor determinant. The minor determinant comes from crossing out the row of the column, so here is E, F, H, I. Then, minus B, for example. B, because there's a minus associated with it, B multiplying the minor determinant, right? D, F, G, this is G. Let's try to make it more different, right? Maybe like that. D, F, G, G, I. My bad, sorry about this. Okay, this is my calligraphy, as usual. All right, and then finally, plus C, then it's minor determinant, right? Which is D, E, G, H. And then, of course, this determinant's 2 by 2. You can use arrows, no problem. So this is EI minus FH, okay? Minus B, DI minus FG, plus C, DH minus EG. That's the way you do determinants, okay? Hopefully you remember that, and that works for higher dimensions, 4 by 4 and everything. I can find the eraser, it's here. All right, so let me, I don't actually need the eraser. Why do I need the eraser if I can do this? All right, so let's do an example without concrete numbers first to get an abstract example, and then we'll do examples with numbers that will look like exercises. Typical example is, for example, this one. I'm gonna give you. All right, find or determine the stability conditioning of, and I'll give you AX fourth derivative, A0, just to do it with this notation, A1X third derivative, plus A2 second derivative, plus A3 first derivative, plus A4 zero derivative equals 0. All right, so what are the conditions for this to be stable, or BIBO stable? All right, remember, for the system to be BIBO stable, I need that the roots of the characteristic polynomial, all of them have negative real parts. So I need that the roots of the characteristic polynomial, which is A0 lambda to the power 4 plus A1 lambda to the power 3 plus A2 lambda squared plus A3 lambda plus A4. I need that the roots have only negative real parts, but that's fine because I have this theorem. Cool. If I build all the delta k's and all the delta k's, all the determinants are larger than 0, this thing will have only negative real part roots and the system would be stable. So let's compute it. All right, the first thing we check is delta 1. Well, delta 1 is very easy because it's 1 by 1. Remember, every k, delta k has dimensions k by k. So this is just A1. So the first condition is that A1 has to be positive. That's the first condition. If you look at A1 and it's a -7, system is not stable. All right, wonderful. So next, the next one is that delta 2 has to be larger than 0. All right, so what is delta 2 here? Well, delta 2 is this one. Okay, well, again, use the rules. The rule says start with A1 in the corner, increase by 2 to the right, A3, decrease by 1 going down, A0, A2. The determinant is A1, A2 minus A3, A0, and that thing has to be larger than 0. That's another condition, all right, for this system. All right, let's do delta 3. Delta 3 is simply, well, it's going to be this one, but we constructed, it's going to be that one, but we constructed with the rules. A1, increasing by 2, going to the right. A3, A5, but A5 doesn't exist in our system, so it's 0. A1, A0, then A minus 1, that's a 0, okay? You cannot go negative in the indices here. A2, A4, A1, A3. Okay, this is determinant. So pick a row or a column. For example, let's pick this column. So we get A1 with a plus sign, and the minor associated with that is A2, A4, A1, A3, right? And then A0 with a minus, and the minor here, we cross just to see it more clearly, is A3, 0, A1, A3. All right, so this thing is A1 multiplied A2, A3 minus A4, A1 minus A0 multiplying A3 cubed, because 0 times A1 is 0. That has to be larger than 0. And then finally, we have another condition. But the other condition is actually becomes very simple. You think, oh, it's 4 by 4, it's the most difficult one. Not quite. Let's write it here. Delta 4, it's equal to, let's build a determinant just for fun. A1, then increasing by 2, A3, remember, and then A5, 0, there's no A5, A7, 0, A0, 0, 0, then increasing by 2, or decreasing by 1 here, A2, A1, A0, increasing by 2, A4, A3, A2, and increasing by 2, A6, there's no A6, 0, A5, there's no A5, 0, and A4. The nice thing is that this determinant, I can take this column, it's kind of on purpose, there's only one contribution, and the sign is plus, minus, plus, minus, plus, minus, plus, okay? You could have started from here, but it doesn't matter. So this thing is A4 times the minor determinant. What is the minor determinant? It's this one. But this one is A1, A3, 0, A0, A2, A4, 0, A1, A3. Oh, does it look familiar? Well, it does, because that's delta 3. So this thing is just A4 delta 3 has to be larger than 0, but we know that delta 3 already has to be larger than 0, so this translates into A4 being larger than 0. For this system, you can check already if A4, the independent term, is less than 0, then you know that the system will not have negative real roots, all of them, and therefore you know that the system won't be stable. So those are the conditions for this generic example of order 4. Let's do concrete exercises for this, shall we? All right, let's do it. All right, let's investigate the stability of this equation. It's a third order equation. So first thing, the characteristic polynomial. That is lambda cubed plus 6 lambda squared plus 3 lambda plus 2. All right, so that's the characteristic polynomial. So that means that, as we say, so let's just write the coefficients. That means that A0 equals 1, A1 equals 6, A2 equals 3, and A3 equals 2. All right, so let's build the different determinants, the minor determinants here for the Hurwitz criterion. So delta 1, remember, is just A1. And in this case, A1 is 6, which is larger than 0. So, okay, for now, it might be stable. Wonderful. Let's check delta 2. Delta 2, remember how we build them? It's a 2 by 2 determinant. We start from A1. We increase 2 to the right and we decrease 1 going down. A1, A0, A3, A2. All right, remember that, okay? So, what is this determinant? This determinant is 6, then A3 is 2, A0 is 1, and A2 is 3. If I'm copying it right. A1 is 6, A3 is 2, A0 is 1, and A2 is 3. All right. This is an easy determinant, is 6 times 3, so 18, minus 2 times 1, minus 2. So 16, larger than 0. So we're in business. The system seems to be, for now, stable. So delta 3 decides here. Let's compute delta 3. Delta 3 is, now remember how we build it again? A1, then to the right A3, it will be A5, there's no A5 here. A0, A minus 1, there's no A minus 1, A2, A1. Now to the right, that would be A4. Well, there's no A4. Okay, and then to the right, that would be A3. All right, that's the determinant delta 3 for this case. All right, let's compute it. So let's take this column, for example, and then we get A1. Well, let's substitute by the values, okay, to make it more concrete and simple. A1 is 6. A3 is 2. Then 0. A0 is 1. A2 is 3. Then 0. Then 0. A1 is 6. And A3 is 2. Alright. So let's pick this column because it's very simple. So 6 times the determinant 3, 0, 6, 2 minus 1 times the determinant, doing that one, right? Let me just do it. That would be 1 minus 1 the determinant of 2, 0, 6, 2. Pretty simple. So this is 6 times 3 times 2 is 6. 6 minus 0. Alright, 0 times 6. Minus 1 that I don't write, this is 4. 4 minus 0. Alright, so it's 36 minus 4, which is 32, which is larger than 0. There we go. So, lambda 1, delta 2, and delta 3 are all larger than 0, which means that the roots of, let's call this characteristic polynomial 1, the roots of 1 have real negative parts, and that means the system is BIBO stable. Or yes, you can write stable, and it's fine with me. And that's the solution to the exercise. As you can see, not too difficult. All right. This is much easier than trying to find the roots of the polynomial and see what they are and what the real parts are. All right, let's do another example. All right, we have a fourth order equation now. X fourth derivative plus 2 third derivative plus 4 second derivative plus 7 first derivative plus 3 0 derivative equals 0. So first, the characteristic polynomial is lambda to the 4 plus 2 lambda cubed plus 4 lambda squared plus 7 lambda plus 3. So the coefficients are A0 equals 1 from this one, A1 equals 2 from this one, A2 equals 4 from this one, A3 equals 7 from this one, and A4 equals 3 from this one. Therefore, the determinants for Harvey's criterion are, let's say, first delta 1, which is just A1. That thing here is A1 is 2. Okay, so it's larger than 0, so that's fine. It could be stable. All right, let's compute delta 2. Let's do it next here. Delta 2, remember the rule. A1 here, then increase by 2, A3, and reduce by 1, A0, A2. All right, so if we substitute, A1 is 2, A3 is 7, A0 is 1, and A2 is 4. A1 is 2, A3 is 7, A0 is 1, and A2 is 4. All right, so if we do this one, it's 2, okay, right, 2 times 4 minus 7 times 1, right, so it's 8 minus 7, which is 1, which is larger than 0, so okay, the system could be stable. All right, let's compute the third determinant, delta 3. You see, remember, to be stable, all of them up to delta 4 have to be larger than 0. Delta 3, so remember, delta 3, the trick is A1 increasing by 2 to the right, so A3, A5, there's no A5 in this one. Okay, nice, so 0. And then I get here A0, then 0, and then here A2, A1, all right, I increase by 2, A4, and I increase by 2, A3. All right, so let's substitute by numbers, and we get the following. A1 is 2, A3 is 7, A0 is 1, A2 is 4, but that should be the same as this, okay? So yes, perfect. Now, a 0 in here, and then A4 is 2. All right? Oh no, A4 is 3, my bad. Okay? Right. And then 0, then A1 is 2, and A3 is 7. All right. Just checking quickly, A1 is 2, and A3 is 7. Very well. All right, so let's pick this column here. So we get first 2 times the determinant doing this one, right? So that will be 4, 3, 2, 7, then minus 1 times the determinant, we do that, right? Times the determinant, 7. So I'm canceling and picking this one. So it's 7, 0, 2, 7. All right, let's do this. So we get 2 times 7 times 4, so 28 minus 6, all right? Then minus, and then this thing is 7 times 7, which is 49, minus 0. All right, so this is 22 times 2 is 44, equals 44, minus 49, equals minus 5, less than 0. This doesn't satisfy Hurwitz's criterion. So we got delta 3 less than 0, therefore Hurwitz criterion not satisfied. That means there are 0 solutions that are exponentially growing, or well, no, that are not exponentially decaying. So the system is BIBO unstable. This is one of those systems that may explode on you. All right, not too difficult, right? Let's do more. All right, so this is as difficult as it gets. This is the most difficult possible. If I ask you this to yourself, usually I don't have 2 parameters but 1, but this is an example of how difficult it can get. So here I'm not asking you if an equation is stable or not, is for what values of the parameters alpha and beta, the system is stable, okay? Now the first thing is the characteristic polynomial, of course. Characteristic polynomial, that thing is lambda to the 4 plus lambda cube plus alpha lambda squared plus beta lambda plus 1. All right, so that means, writing it here, that A0 is 1, A1 is 1, A2 is alpha, A3 is beta, A4 is 1. All right, sorry about this. Sorry about this. Okay, so right, so let's build the different determinants and then find the conditions for alpha and beta so that the system is stable. First, lambda 1, very easy. Lambda 1 is just a 1, which is equal to 1, is greater than 0, so that's fine. All right, lambda 2, remember what it is A1, then increasing 2 to the right, A3, and 1 decreasing down, A2. So what we get here is A1 is 1, A3 is beta, A0 is 1, and A2 is alpha. So that means that alpha minus beta has to be greater than 0. Oh, first condition we need to satisfy. Alpha minus beta has to be greater than 0. Or in other words, let me write it simpler. We can simplify this to alpha has to be larger than beta. That's the first condition. Okay? All right. Delta 3, remember the rules. A1 increase to A3, A5 does not exist. A0, 0. Then A2, A1, A4, A3. All right? So let's substitute. And we get A1 is 1, A0 is 1, 0, A3 is beta, A2 is alpha, A1 is 1, and then 0 here, A4 is 1, and A3 is beta. Right? So this determinant is 1 times, this one is alpha 1, 1 beta, minus 1 is this one, right? So it's beta 0, 1 beta. All right, so that one is alpha times beta minus 1 minus 1 times beta squared, so minus beta squared. All right, that has to be larger than 0, which means that alpha beta minus beta squared has to be larger than 1. Now we can divide by beta to simplify, but remember that you have 3 cases. Well, we have to divide 3 cases. Remember what happens depending on the sign of beta. So if beta is larger than 0, if beta is equal to 0, if beta is less than 0, it would be different. You can see already that for beta equals 0, you get 0 larger than 1, that is not true. So you get 0 larger than 1, that is not true. So beta cannot be 0. This case cannot exist. Okay, or cannot exist, I mean you don't satisfy this for beta equals 0. All right, so now I'm going to divide by beta, but remember that when you have an inequality like 2 is larger than 1, if I multiply both sides by a negative number, for example, multiply by minus 2, that will be minus 4, and then minus 2, I need to invert the sign of the inequality, right? Minus 4 is certainly below minus 2, okay? So remembering that from your high school calculus, right? With positive beta, I divide by beta, I don't change any signs, I get the inequality alpha minus, divide by beta, right? Alpha minus beta has to be larger than 1 over beta, okay? And this one would be alpha minus beta has to be less than 1 over beta. And beta is negative because I have to invert the sign of the inequality. All right, wonderful. So the last one is delta 4. But that one would be simpler, as we actually saw. Let's repeat it here. So that one, if we have to build it, it would be A1, A3, 0, 0, A0, 0, 0, A2, A1, A0, and then here A4, 0, A3, A2, A4, 0. All right. So the easy thing is that here we can just check and take this column, plus, minus, plus, minus, plus, minus, plus. So this thing is just A4 multiplying this determinant, right? Well, I'll write it A1, A3, 0, A0, A2, A4, 0, A1, A3, but that is just A4 delta 3. So the condition is that this has to be larger than 0, but of course if we already have to satisfy that delta 3 is larger than 0, the extra condition that this gives is that A4 has to be larger than 0. Now A4 here is 1, 1 is larger than 0, so yes, that is always satisfied. Alright, so we compile the conditions that we have. Look what we have. Let's start from B less than 0. For B less than 0, the condition that we have there is that alpha minus beta is less than 1 over beta. Right, but if this is true, this is a negative number, right? 1 over beta is a negative number. So 1 over beta is actually less than 0 because it's a negative number, because beta is less than 0, so 1 over beta is also negative. That means that alpha minus beta has to be even less than 0. So that means that alpha minus beta has to be less than 0, has to be negative, right? Because it's even more negative than this already negative number. Okay, but if we go to the first equation gives me that, let's call this one condition 1, and this one condition 2a, and this one condition 2b. So we have 2a right here, and then condition 1 tells me that alpha minus beta is actually larger than 0. So condition 2a says alpha minus beta is less than 0. Condition 1 says alpha minus beta is larger than 0. Incompatible. Incompatible. What does that mean? Well, it means that beta cannot be less than 0. The only room now for having some region of stability is when beta is larger than 0. Okay, let's see if that can be. For beta larger than 0, then identity 2b gave us that alpha minus beta is larger than 1 over beta, so it's positive. And indeed, 1 tells me that alpha minus beta is larger than 0. Okay? So you can tell this condition, alpha minus beta larger than 1 over beta and alpha minus beta larger than 0 are compatible at the same time. I mean, it doesn't need to be, there's no one that's more exclusive than others, so the solution would be in the intersection of these two regions. Okay? So what would be the intersection of these two regions? Think about it for a second. Have you thought about it? Okay. So I would be content if this were an exercise for you, if you tell me that the region is the values alpha, beta in the intersection of alpha minus beta larger than 1 over beta and intersection alpha minus beta larger than 0. You have to satisfy these two conditions. You could even give me an example. For example, alpha 100, beta equals 1. Certainly you can check that satisfies both of them. Alpha is larger than beta, and alpha minus beta 99 is larger than 1. That's 1 over beta. So that would be two values for which is stable. Now, if you want to get fancy, we can plot that region and see what region it is. Let me clear the space over here a little bit to plot. Okay, that's clear. Before I say anything, okay, it's important that you remember that beta also has to be positive. Okay, I didn't write that. So intersection with beta positive to be complete because I had it in here, but I didn't specify. Okay, so let's plot the region satisfying that. So let me write here the beta alpha plane to get the region. Now, the region of, let's call this condition in blue, it's alpha larger than beta. All right, well, alpha larger than beta is this region. Oh, this is dying. I'll get another. So it's this whole region. That's the region of space where alpha is larger than beta, right? Okay, now, the region beta larger than 0, let's notate this one in black, why not? Beta larger than 0. That one is saying this area. All right. And then finally, so whatever it is has to be in this intersection. But then we have a final region, which is this one. I'm going to do it in red. This one, that is alpha is larger than 1 over beta plus beta. Okay? And this is a conic section that is actually easy to represent, completely asymptotics, to see what it does. What does it do when beta goes to infinity? When beta goes to infinity, it goes to, so what, we have to plot this curve. Alpha equals 1 over beta plus beta. Okay, when alpha goes to infinity, when beta goes to infinity, this goes as alpha equals beta, because this is negligible. So that means it goes to here. So it comes from infinity like this. Actually, next to it, right? Like that. Okay, what does it do? When beta is 0. When beta is 0, boom, alpha goes to infinity. So as it goes to beta 0, so it's decreasing. So there's some point in which it will hit here and then suddenly go up to infinity. Okay, so this area is that. Whoa! What happened? Oh, a distortion of the space-time continuum. Well, it was convenient because it cleaned a little bit the board. And, let's go with it, okay? So what I was telling you is that that region is that one, right? And the solution is, of course, the intersection of beta larger than 0, alpha larger than beta, and alpha larger than 1 over beta plus beta, okay? So if you want to formally write this solution, again, that is not necessary for an exercise, and for an exercise it will never be so complicated, but the solution is the set of pairs beta alpha such that they are in the intersection of beta larger than 0, alpha larger than beta, and alpha larger than 1 over beta plus beta, that is represented here. Notice that this one is not really necessary. I mean, it is necessary because if there could have been some for beta less than 0, but we didn't get it, right? But to write the solution is not necessary because this one, right, the intersection of these two is already fully contained in beta larger than 0. So for the solution, you don't need to write that one, okay? All right, so that's the solution to this exercise. This is as difficult as it gets. In fact, it's not gonna get as difficult as that for you. Usually, there will be, if I ask you to determine the stability for what values of a parameter the system is stable, it would be only 1, not 2. But it's good that you practice this and then you remember how to operate with these things and inequalities and so on. All right, so this is all for the stability topic. I hope that is all understood, but if not, as usual, please bring all your questions to the review session. And in the next video, we're gonna start the block on Fourier analysis. We're gonna begin with the Fourier series and understand a little bit what is that business. All right, I'll see you there.